All right, so thank you. So as you just heard, my name is Noah. I'm a PhD student at the Software Languages Lab at the Vrije Universiteit Brussels. And today I will talk about our work on garbage-free abstract interpretation through abstract reference counting. So I'll start with the context here, which is abstract garbage collection, and explain why we need it using a motivating example. So we have a very simple scheme program here, one that has a double function, a square function, so an apply function. It applies double to 3, applies square to 4. And let us say that we want to analyze this program using an abstract interpreter that does not employ abstract garbage collection. So let's see what happens. So we start with the first function call here, applying double to 3. So of course, f gets bound to the double function and gets bound to 3. Now, for the sake of the example, let us also say that we're going to use a context-insensitive analysis, which means that we're not going to distinguish different calls to the same function, right? So when we get to that second function call there, we're going to have to merge together the argument values for f and n, so that f is either going to be the doubles function or the square function, and n is going to be either 3 or 4. Now, of course, this introduces a certain imprecision in the analysis, because right now, when the abstract interpreter needs to evaluate f of n, it has to consider every possible combination of having either double or square as the operator f, and 3 or 4 as the operand n. And well, that gives you the following imprecise result for this program. That imprecision also hurts the performance of your analysis here, because, well, to analyze f of n, we had to analyze both a call to the square function as well as a call to the double function, whereas in a real execution of the program, you would never have this call to the double function. So that's what we call an infeasible path, and they hurt performance because the analysis is just wasting its time on the exploration of such infeasible paths. So let us now retake this example, but this time using an abstract interpreter that does employ abstract garbage collection. And so we start off in the same way, f gets bound to double, n gets bound to 3. But let's say that when we get to the second function call now, that some oracle would appear and tell us that now would be a good time to apply abstract garbage collection. And so abstract garbage collection is basically just the application of garbage collection to an abstract interpreter. It means that we can reclaim all the addresses that are no longer reachable in the abstract interpreter. So here, when we get to that second function call, neither f nor n are still in scope with respect to the environment and runtime stack of the abstract interpreter, so they can be reclaimed. That means, of course, that when we now resume the analysis and we do the second function call, that we no longer have to merge together with those old garbage values, and, well, therefore we also don't have that same precision loss. So abstract garbage collection really helped to increase the precision of the analysis here, because we can now precisely determine the value for this program. And in this case, it also helped the performance of the analysis, because we no longer waste time on these infeasible paths. The problem is, of course, that in real life, this oracle I just showed you doesn't exist. So you don't really know when you need to apply abstract garbage collection. Notice that in the previous example, it was really necessary to apply the abstract garbage collection right after the first function call, but before the second one, in order to avoid a precision loss. But needless to say, in general, this is something that you don't know beforehand. So you'll have to decide on some kind of policy that tells you how often and when you're going to apply abstract garbage collection. So what are your options? Well, you can try to play on the safe side and avoid imprecision by applying garbage collection very frequently. But of course, as you know, garbage collection has its own overhead, so I don't need to tell you that frequently applying abstract garbage collection, that's also going to hurt the performance of your abstract interpreter. Now, on the other hand, if you try to avoid that overhead by applying abstract garbage collection less frequently, well, then of course you end up with a problem that we saw in the example. You might not be able to reclaim that garbage before it causes imprecision in your analysis. And more often than not, we see that this kind of imprecisions, they also lead to a decrease in performance. So in an ideal world, you really want to avoid those negative effects of garbage. You want to keep your abstract interpreter what we call garbage-free. So garbage-free means that you always immediately eliminate the garbage, so that you're basically guaranteed that garbage is never going to disrupt the behavior of your analysis. Now, if you never apply abstract garbage collection, of course, you're not going to be garbage free. Of course, you're also not going to have any GC overhead. On the other hand of the spectrum, if you apply it at every step of the abstract interpretation, then by design you're going to be garbage free, but of course you're going to have a lot of overhead from those frequent GC applications. Now you can of course make a compromise, which is for instance done in the TAGS frameworks or other related work, and apply abstract garbage collection less frequently, for instance at every function call. If you do that, then you'll be able to reclaim a lot of the garbage, but in general you're not going to be garbage free. Similarly, you're going to reduce a lot of the overhead by not applying it at every step, but in practice there's still going to be a significant amount of overhead. And so what we're looking for in this work is something that can give us the best of both worlds. Something that can give us the full precision and performance benefits of garbage-free abstract interpretation without that significant cost in overhead. And for that, we propose abstract reference counting. So similar to how abstract garbage collection is the application of garbage collection to an abstract interpreter, abstract reference counting is the application of reference counting to an abstract interpreter. Now, why are we looking at reference counting here? Well, basically because reference counting has a major advantage in that it is continuous in nature. With that, we mean that when you're doing reference counting, your garbage is going to be reclaimed as soon as it pops up. And that's, of course, exactly the property that we're looking for in order to keep an abstract interpreter garbage-free. It means that we no longer need to ask the question when to apply abstract garbage collection, because the reclamation of garbage is continuously interleaved with the abstract interpretation of your program. Reference counting also has a relatively low overhead. Of course, there's certain overhead attached to storing and updating the reference counts. But generally speaking, in the context of an abstract interpreter, such kinds of overheads are not going to be all that outspoken. Of course, as you know, reference counting also has a few things going against it. Most notably, it's not able to deal with cycles, and therefore abstract reference counting can, well, at least not the naive version of abstract reference counting, cannot reclaim garbage cycles. And I'll come back to this later on, because it turns out that this is actually quite a major limitation when we apply reference counting to an abstract interpreter. So how do we incorporate reference counting in an abstract interpreter? The basic idea is that we can keep track of those reference counts at the level of abstract addresses. So what we do is we add a component to the abstract interpreter, the one that's highlighted in gray there, which for every abstract address will keep track of the set of incoming references from other abstract addresses. So the set of references for a given address L is basically the set of addresses whose abstract value at that location directly refers to L. So once you no longer have any references to L, this set will be empty and L can be garbage collected. A small side note, notice that even though we added a component here, we didn't actually increase the complexity of the analysis, because, well, this new component is defined entirely in terms of the existing components in the abstract interpreter. And then what's left to do is to adapt the abstract semantics, of course, to ensure that we correctly maintain the references for every abstract address, and to ensure that an abstract address is reclaimed as soon as it no longer has any references. So if we look back at our table here, where can we put abstract reference counting? Well, like I said, it has a relatively low overhead, but unfortunately it's not yet garbage free because of those cycles. Abstract reference counting can't reclaim garbage cycles, therefore it's not going to be garbage free. Now, you might say that this is not that big of an issue, because we know that for many applications and programming languages, like functional languages, cycles tend to be quite rare. However, that is no longer true when we look at it in an abstract interpreter. So it turns out that cycles are actually much more common in an abstract interpreter, and to see why, I'll just give you a very simple example. So say that in the concrete we have 5 addresses, A1 through A5, and well, we draw an edge between 2 addresses when one address points to another one. Clearly, no cycles in the concrete here, but when we have to abstract these concrete addresses, then it might be that 2 or more concrete addresses are going to be abstracted by one and the same abstract address. And so let's say that, for the sake of the example here, A2 and A4 are going to be abstracted by the same abstract address. Now what happens then is the following, because in the concrete A2 points to A3 and A3 points to A4, in the abstract we'll see that the abstraction of A2 points to the abstraction of A3 and the abstraction of A3 points to the abstraction of A4. And you can clearly see that this of course creates a cycle in the abstract. Actually this is what we call an artificial cycle, because it's a cycle that you would never see during a concrete interpretation of the program. It's something that occurs only as an artifact of the abstraction, hence the name. Now the problem is that these kinds of artificial cycles, they occur very frequently during abstract interpretation, and abstract reference counting is not able to reclaim them once they become garbage. So to overcome that issue, we extended abstract reference counting with a cycle detection algorithm so that it can reclaim all garbage cycles. Now, basic idea of this algorithm is that we will no longer keep track of the reference counts at the level of individual abstract addresses, but rather for strongly connected components of abstract addresses. Now, due to the time limit, I'm of course going to have to refer you to the corresponding section in the paper if you want more details on that algorithm. Needless to say though, in theory, adding cycle detection to abstract reference counting, that's going to incur a certain overhead on our approach, but in practice we can argue that it's still going to be reasonably efficient for an abstract interpreter. In fact, we were able to show formally that for certain parts of the store, like the continuation store, the addition of cycle detection only incurs an O of 1 amortized overhead. So it's pretty cheap. This is something that we also evaluated empirically by actually verifying that once we add the cycle detection, it doesn't actually increase the GC overhead. But the most important takeaway message here, of course, is that once we extend abstract reference counting with this cycle detection, we end up with a garbage-free abstract interpreter. And so if we go back to our table here and we add the cycle detection to abstract reference counting, then we end up with something that is garbage-free while still having a relatively low overhead. So let us now validate those claims by well, comparing a few of these approaches in terms of precision and performance. So we're going to start by looking at precision. I have a few benchmarks here from the Gabriel benchmark suite in Scheme, as well as a few other ones that are commonly found in related work. And we're looking at 4 different configurations here. One that never applies abstract garbage collection, one that uses the policy that you most often find in related work, applies garbage collection frequently but not at every step. Then one that applies it at every step, and finally our own approach using abstract reference counting with cycle detection. So for precision, we're going to look at the number of states that are explored by the abstract interpreter. Generally speaking, a lower number of states is an indication of higher precision, so lower is better here. If you look at the results, then, well, you can see it quite clearly that without any abstract garbage collection, precision is quite terrible. Because we have a big number of states to explore. This is what we often refer to as state explosion. The reason for this state explosion is quite straightforward. Because we don't collect any garbage, we get imprecision. This imprecision translates into infeasible paths, and those infeasible paths lead to more states being explored than what's necessary. Another thing that you probably notice is that our own approach with abstract reference counting and the one that applies garbage collection at every step achieve the same precision for nearly all benchmarks. This is not a coincidence. The reason, of course, is that both of these approaches are garbage-free, and therefore they can achieve that same optimal precision. If we apply garbage collection less frequently, like the one in related work, then we can still get decent precision, as we see, especially compared to the one that doesn't apply any abstract garbage collection. But there is still a significant difference, I would say, with the optimal precision for certain benchmarks like the puzzle benchmark. So that's precision. Let's also have a look at performance here. So for performance, we're again looking at the same benchmarks, same configurations, and this time we're going to look at the total analysis time measured in milliseconds. So again, lower means better here. Now notice that overall performance is actually going to be affected by 2 factors. On one hand, the precision, because that determines the number of states that you need to explore. And on the other hand, the GC overhead, because that determines the rate at which those states can be explored. Again, looking at the results, we see that without any abstract garbage collection, our precision is quite terrible. That's of course due to that aforementioned state explosion, which causes the analysis to explore a lot more than necessary. You can clearly see in the puzzle benchmark, for instance, that it times out after 30 minutes, whereas all of the other configurations can terminate on that benchmark within 30 seconds. So we can drastically improve performance by applying abstract garbage collection, because then we have fewer states to explore. Interestingly enough, though, the one that applies garbage collection less frequently always has better performance here than the one that applies it at every step, despite the fact that it has a larger state space to explore, and that's just because it applies abstract garbage collection less frequently, and therefore it has a lower overhead. So if you look at our own approach here, well, we already knew that we had the optimal precision, and it turns out that we also have a relatively low overhead, and well, therefore we always get for these benchmarks the best performance. So compared to the policy of the related work, we already had better precision, we have a lower overhead, and therefore significantly better performance. And if we look at the one that applies garbage collection at every step, so the one that has the same optimal precision, then we often see a performance improvement of an order of magnitude. So not only do we achieve that optimal precision, but we also outperform the other configurations here in terms of performance. So we implemented abstract reference counting with cycle detection, as well as the other existing approaches to abstract garbage collection as an extension to Scala-AM. So if you don't know, Scala-AM is an open source abstract interpretation framework that is implemented in Scala. We submitted our implementation and the evaluation as an artifact. And if you want to try it out, then you can also find it on the GitHub link here shared below. So in conclusion, I talked about garbage-free abstract interpretation, which significantly improves both the precision and performance of an abstract interpreter. I then introduced abstract reference counting as a novel approach to efficiently design such a garbage-free abstract interpretation. However, I also explained that without any cycle detection, abstract reference counting is not able to reclaim garbage cycles like those artificial cycles. Therefore, we had to extend it with a cycle detection algorithm so that at the end we could unlock the full benefits of garbage-free abstract interpretation without a significant overhead cost. So that concludes my talk. Thank you for listening.
Thanks for the talk. I did not understood in the evaluation in the number of states how it is possible when you apply the garbage collection at each state that you get some larger numbers than actually applying your...
yeah, I kind of expected that question, to be honest. So indeed, in theory, these two configurations should get the same number of states because they're both garbage-free. However, in practice, it turns out that our implementation sometimes takes more coarse-grained steps than what you would consider the atomic steps, and therefore it doesn't actually apply abstract garbage collection at every step. So that's why you sometimes, with the GC at every step, you sometimes don't get the same optimal precision. But that's purely a technical implementation detail of the Scala-AM framework that we're using.
Thanks for the talk. I'm interested in this claim of garbage freedom. I'm wondering if I have a reference to something stored in a variable, and that variable is still in scope, so I haven't freed it or left the block, but I'm not going to use that variable anymore. It's no longer live. Do you count that as garbage, or not until it goes properly out of scope?
Well, we define garbage as things that are still reachable from within the abstract interpreter, so it might indeed be that some things are still going to be reachable while they're not going to be used. You could optimize this by, for instance, trimming the lexical environments that are stored in closures so that you're actually going to have less reachable addresses. But yeah, our definition of garbage is really based on reachability and not usage. There is related work that focuses more on, that basically says that garbage is what you're no longer going to use at a further point in your program. But that's basically a different definition of garbage. Okay. We found that in practice this is a pretty efficient definition.
Okay. So, okay, thank you. So I guess the garbage freedom then is a slightly moving post, as it were.
If you improve your definition of garbage, you're also going to improve your definition of garbage freedom. Yeah.
Great, thank you.
One final question.
Thank you. I really enjoyed this talk. One question I have is, how big are these benchmark programs?
Oh, okay. Well, they're not that big. They're what you could consider micro benchmarks. I think in terms of lines of code, they range between 50 to like 500 lines of code, but like the average is more to the lower side there. But yeah, it's what you can expect for these kinds of techniques to abstract interpretation. It's what you often see in related work as well. We also focused on like the basic version of AAM, so that's of course not as powerful as more advanced versions, but we wanted to keep it as simple as possible, well, without introducing unnecessary complexity.
Okay, let's thank Noah again and get the next speaker.